Alright, welcome back to the Cymax channel. Today I'm going to build on the last video we talked about joblib and explore a new direction in hashing and caching for saving persistent data. And we'll see how that gets us closer to fair but not quite fair. And but I think it's going to end up being a good trajectory to get us there in another video or two. So last time we talked about joblib, and let's go ahead and find it, what we did. So this is like a dynamic table of contents that is built into Cymax, where you can jump to a heading in any org file in a project. And this is a project, this is my scientific notebook, electronic lab notebook project, and so we can jump around to any heading that's in there. So just to remind you, what we had tried to do is use joblib to make a cache. We write a function that has an argument k and it returns some values, and we decorate that function with a cache decorator, and that takes our function, wraps it in some new code that will make a hash of the arguments and the source code, and then it will store the output in a pickle file. And it worked pretty well, but I showed you there's some issues with the way it uses a path here, where it tries to find the path of the module containing the Python code. And since we're running this in a notebook, it exists in under main, and then this path is some kernel directory in a temp place that isn't portable, and we ended up getting lots of directories that I think shouldn't have been there. But it did work in the sense that you could store and retrieve the data. The data stored in pickle form, so it wasn't interoperable. But we did find some ways that we could search it, and it was a little bit tedious, but it works. And then I showed you a couple of limitations that if you try to run it different ways, like running exactly the same code through a Python script, ends up running the code again. So that was somewhat undesirable to me. And there's some other limitations that I showed you if you make internal changes to a function, or if your function's not really pure, like it reads from a file and you change the file, then that does not invalidate the cache. Cache invalidation is considered one of the harder problems in computer science, so you should tread very carefully when you rely on a cache to know when it's right or not. Okay, so today I want to jump to a new journal entry. And we'll start using hashcache. And I'll tell you about hashcache after we look at some ways to use it. In the meantime, we will talk about some applications of it. Alright, so today I want to talk about using hashcache, and hashcache is a library I wrote for pycse specifically to address some of those issues with joblib. It actually uses joblib under the hood in a couple of ways, and so let's just go ahead and get started and have a look at some of the benefits of it. Alright, so we say from pycse.hashcache. Actually, let's have a look at a blog post I wrote on this just to remind me exactly what kinds of things we need to do. Alright, so we're going to have pycse.hashcache import hashcache, and then we're going to use a hashcache decorator, and it looks like that's maybe all we have to do. And this is a hint that there are other ways we can use hashcache, but we're going to look at the default method first. Alright, so we import that, wait for my kernel to get started, and let's do, I'm just going to do some simple functions here. and then we'll have a look. Let's make that little sound again because I like hearing it. Let me make this a little bit bigger. I think it was in here. There it is. All right, so this is going to play a little sound, and I'm just going to make it return A and B. Very simple little function, and then I'm going to decorate it. Let's say hashcache. I think I have to make this a function right now, like that. Why is this doing this weird thing? All right, so that's going to make it, and now if I just call this with, say, f of 1, you heard a little sound, probably, and let's already look and see what got created in here. So we have a cache directory, then there is 61, and then there is this hash. That's a single file. You might recognize that as something like a SHA1 hash or an MD5 hash. And then if I open this, it is obviously storing some binary bytes, and those are just going to be a pickle string. Okay, so it is still storing pickle. That means we're still not quite interoperable, and actually it looks like it's even less searchable, but we'll see in a minute if that's still the case. And now if I run f of 1 again, then we just get the answer that we're looking for. So let me come up here and change this signature to be verbose equals true, so we can see a little bit more about what's happening. And here it shows you in verbose mode, this is what gets pickled. So there's actually quite a lot of information that ends up getting stored here. When the information is in here, we have the arguments that got called, and it's interesting, here we have 1, but if you look down here, there are standardized keyword arguments that you can see, so it even captures the default values of B that were done, and it tells me when I ran it, and it has the output, and it has some information about some other things up here. Okay, so that's the data that gets stored, and if I run, let's run another one here. So let me say here, if I just put a 1 here, it also just returns the lookup value. So that's nice, even though I sort of changed the signature, the arguments, it's okay, and I can use keyword arguments in any order, and that also simply looks up the answer and doesn't change anything. Now, this is a little bit of a dilemma. If you are running an experiment, you may want to rerun and make sure that it is repeatable and not simply look it up. And so we don't have a solution for that the way this function is written. And you could, I don't know if there's an obvious way to force it to rerun, but usually what I would do is make an optional argument that has a tag or a string, and you would just increment that version. And now if I make this 10, you'll hear a ka-ching again. There it is. And it should give us some new output, and it says that it wrote the cache. So I follow like some inspiration from Git in using the first 2 characters of the hash to break up the directories, so we don't end up with a million files in a single directory. It will just get, there's a lot of options. There's 26 first letters and 10 second numbers, and so there's a lot of possible combinations that will get in there. And then when you want to look it up, you simply calculate the hash and then look for this path. So it's pretty straightforward to do. All right, let's have a look again and what's in our cache. We see we have two subdirectories now, and there's just the two functions that get written in there. All right, so this solves one of the problems that we saw before, I think, and we have more information that's stored. You can iterate through all of these cache directories to get all of these files, and then you could load them. Let's see if we can see how that might work. Import glob, glob.glob. I think we can just do cache ***. Let's see what comes out of that. Oh, yes, star. So these are the hashes, and then I might say for f in that. Let's import joblib. I think we can just do joblib.load f. Let's just print that. And there's the output, and so you could iteratively and manually by brute force search through all of these. So let's say I wanted to find out anywhere that say a was equal to 10, then I would for this I would say if, let's make this the data equals this, and then if data standardized keywords, make that a string, dot get. This is the most reasonable way to do it. That way, if there's other functions in here that don't have a, we're in there, then we would not get an exception. Then we can just say print data, and that will find this particular one like this. So I'd say this qualifies as findable for a small number of runs, even a few thousand. You could just brute force search through here, and you could find whether it was run by me. You could even imagine doing some kinds of queries about by date. You could search by keyword arguments, and you could check for outputs. So you could write your own findable code that way, and that also makes this kind of reusable. You can read this data, etc., and everything should be okay. Let me run another one up here, and let's do some more complicated data structures. So let's do a NumPy array and say f of np.linspace. Let's say just do 0, 1, and I'll just put 5 elements in it. It shouldn't really matter. And that's going to have an array. Let's see, string object is not callable. Did I define f somewhere? Maybe I did something funny here. Oh, yeah. I did something where I redefined f when I iterated, so I probably shouldn't have done that. My mistake. Let me just run this again. And I can delete this now because f should be a function again. And there's our ka-ching. And it says that it wrote this, and this is pretty remarkable because it has pickled an array and saved the array. That's one reason joblib is nice. Arrays are not generally serializable. Let's do something from the atomic simulation environment. From ase.build, import bulk, and let's say that A is bulk copper. And I'll just print A so you can see what it is. It is an atoms object. And so that's a complicated data structure. It's a class, it has some attributes, and we can call f of a here, and we hear a ka-ching, and remarkably it is able to pickle that and save it. And so now if I look down back down here, let's make this let's just put an underscore there so we don't lose our f variable again. If I print this, then we'll see all the things that we've run before. Output, here's one. Here's that atoms object that we stored. That's pretty convenient. All of these things, these are all of the ones we ran. And what I want to show you next is that this also should work when I run this in a Python script. So we're going to do a couple of things here. I'm going to copy this. Let's do it in org mode first. So here we have a Python source block. This is going to write to a temp file, and then it's going to call Python on the temp file. And if I just do Python f of 1, I think I might have to do, let's do results output, and I'll print this. So this should simply look up the values. Oh, but it didn't. It actually ran. That's interesting. I'll have to look at why that happened in a little bit. I really thought that would not have changed, so we'll have to investigate what happened there. Let's try running this as a Python script from a Python file. So to do this, I need to tangle it. And this is a literate programming idea, where from org mode, I'm going to tangle this to, I don't know, ph.py. And then down here, I'm going to make a shell block. And I'll make a variable. And I can make this be org babel tangle. So this is going to convert this shell block up here into a Python script. And then I can just do Python ph.py here. And that did not run a second time because you could hear, you didn't hear it. And it says up here, it's just looking it up and it didn't do any writing. So we have a partial solution to the issue of like portability and running it the same way. If you use exactly the same code, you should get to exactly the same result, whether you run it from Python or a notebook or from a script. That was something that I thought ought to be true. Now, I wrote this code, so obviously there's some flaw in the logic, and I have a good idea of where it is, and when we look at it, we'll see if that's the case. Okay, let's talk about another issue that I raised with joblib. And with joblib, it turned out that if you make kind of trivial changes to your function, that it reruns. So by trivial functions, I mean like if we add a comment or a docstring or something like that, those don't have any effect on our code. And so if I run f of 1, this should simply look up that result. But if I add a docstring, let's see what happens here. What my preference would be, since this is a change to the code that doesn't have any effect on the output, then it should simply look up that cache. There should be a way to figure that out. And that is actually what happens with hashcache. Is it doesn't use the raw code, it uses the bytecode, and we'll look at that. And the bytecode ignores docstrings and comments, and it also ignores things like variable changes. So if you change, if I change A to be X everywhere, joblib would call this a new function, but hashcache considers it, apparently a new function. So that's a little bit surprising. So we'll have to inspect what's happening there. So anyway, these are all things that as you look into any cache solution, you have to know and understand what's happening in there. And going back to our cache, now we have all of these directories that each have, one or more hashes in them. It's possible there could be only one hash in each one for now, but if you end up getting another hash starting with F4, it will be in the F4 directory. All right, the nice thing is this is totally portable. You can move this cache around, and everything should go that way. All right, let's see if we can find the source code for this and see what we can inspect. So hashcache is located here. It's installed in this package like this. So let's live stream this one. So this is a part of pycse that I wrote, and I wrote a bunch of notes here about why I wrote this library and what kinds of things I think would be improvements. So one is the file is a problem. It's not portable. It is different if you run in Python, Notebook, or Standard In. So the cache is not portable with joblib. And joblib uses the function source code, and so if you change any white space, any docstring, any comment, it changes the hash, and that isn't something that I wanted. We'll see if this is still true. My hash is based on the function name, arg name, so I guess I did make a change there. The bytecode, arg values, and qarg values, and then I do use joblib hash for that. So that means any two functions with the same bytecode should cache to the same result. And here's a note. This is still considered alpha, proof of concept. And I think it's important that you test any library because of all the things that we've been looking at. All right, so many functions can run in parallel because we're reading and writing to individual files. So that's the only limitation on running things in parallel. It's pretty portable across machines. I wouldn't expect this to work across different versions of Python because the bytecode might not be compatible, and I rely on bytecode for getting more robustness to changes that don't matter. And you can define your own functions. We're going to do that in another video after we explore, probably in this video, some other ways that we could use things besides pickle. All right, I'm going to scroll through this and get to some of the ways things work. So I use inspect a lot in this library. So if you get a function, the inspect library can give you all of the arguments, the names of the arguments, and then I standardize these so that we get all the defaults that can be stored. Otherwise, you risk defaults changing in the future and things going awry. Getting the hash is one of the most important things. You want your function here to be as pure as reasonable. This hash is not sensitive to global variables, so it's limited to in that way like joblib was. That's a very hard problem to solve because it's very difficult to capture the whole global environment for it. But the gist is we get a function name, we get the function bytecode, we get the standardized arguments, and that's what we build our hash on, and we use SHA-1 for that. You could use some other things, and I think I did try to capture globals before, but I think that's this args here is why that hash changed when I changed the argument names. I used to not do that, but decided to be more conservative, and so it doesn't seem likely you would do this, change those names a lot, but things happen. The hash path is just that hash you split on the first two directory letters. To load data, we just get that hash and then load it with joblib. And it returns two things. And then to dump data, we use joblib as well, and it just dumps it to the hash path. So we're still leveraging joblib a lot. We just change the hash behavior, and that's the most critical part. So the decorator that we use has verbose equal false, and we define loader and dumper functions. So this is where we can change what we do in the future. We don't have to use joblib.dump. We can write data to a SQLite database. We can write to JSON. We can do anything we want, and we'll explore some options for that in another video, because there's a lot of things here. But it's otherwise just a decorator, and a decorator is a function that takes a function and returns a function that has new behavior. So when you call your function that's been decorated, we get a hash of the function and the arguments. We see if we can get the data. That means that it already exists. And if it does, we return it. And if it doesn't, then we run the function. So that happens here. And I do some timing here so we can store it as metadata. We get a hash for it. This does check that the hash hasn't changed. So if you use mutable arguments, for example, if you change the args, then the hash will change, and that's going to just print a warning. And then we construct this dictionary that has the output, the hash, the function name, the module, the args, keywargs, standardized args, hashcache version. I store the current working directory. I think that's a good idea. I'm not positive, but it helps you see like where something was done in case you ever worry or wonder if there was a machine specific issue. I don't store the host name, but we could, and we get the user and some other stuff, and then we just dump that, and that's that. All right, so that's all hashcache is, and that is the main way we can use it. So I'll probably have to re-watch this video to remember all the things that were a little bit surprising. I think when I changed X here, if I had read that beforehand, it wouldn't have been a surprise. But I was a little surprised by one of the Python examples, and should follow up on doing that. So at the end of the day, we have this JSON. This is just a dictionary that's getting stored. So we could directly write JSON to that instead of writing the pickle file. It's just pickles are super easy to use, as long as it's short term and you don't envision having Python change during the scope of your project or during the scope of time you want to be able to load it. And you have no concerns about security, because pickle will create and execute, or certainly can create objects that are executable. And so you can run into some security risks with it. So to move forward a little bit, I'm just going to set the stage here at the end of this video. If we go back to the blog post that I referenced on, then here we have some alternative backends. And the gist of the idea here is that you can define your own dump and load functions. So here I did something for LMDB. It's a Lightning database. You might want to do this if you don't want a bajillion files being created and you want to instead have a database that you can use. So LMDB is one, very fast for lookup, and since we look up based on a hash, it's basically like a persistent dictionary. And so here we have a dump, and so we are just writing the joblib output to it, and that's then we can load it as well. Shelve is a built-in library, so you can use Shelve for that. Here is something with SQLite, so we just, again, I'm just dumping the joblib.dump data directly into SQLite. And I think I want to look at storing this value as this data as JSON, and especially storing it as JSON inside a SQLite database, because that will make it more easy to search, because SQLite supports NoSQL-like JSON. The problem with JSON, though, is let's have a look at serializing data in JSON. So out of the box, we have the JSON library, and JSON has a dump. Let's do dump s, and we can put some data in here. So let's make a dictionary. Let's say A is equal to 1, B, let's put all of the data types in here, a string. Let's do C is, let's do a tuple, and D is a list. And what other kinds of things? Let's just put a number as a key. And what am I missing in here? Let's do another dictionary. And that's probably pretty good. Let's close that. And now if I run this, it's going to convert. Why don't I make this like output raw? Maybe code. That's not very helpful. Oh, results maybe, not output. That's not really presenting the way I thought it would. Maybe I should, what if I print it? That's better. Okay, so this is just converting this dictionary into JSON data. A couple of things to point out. This tuple is represented as a list, and this is represented as a list, so you can't really tell the difference between a tuple and a list. So if that matters, you're going to have some trouble. This 2 gets turned into a string. I don't know if that's a big deal or not. And here we have everything is a string. So even though you're allowed to, oh no, this is also turned into a string. Maybe if I make this a string, let's see what happens. That one's okay. We do get mixed types, but you can't tell the difference. Where we do run into trouble is that if I add an NP array, we're going to get an error, because you can't convert an NP array to, that's even not even a nice error. Somehow we don't get good information about it. So JSON on its own isn't going to be super great for us, because it's not going to be able to serialize the data. Let me see what happens if we, I guess this is also going to be a problem if I solve that IVP, or solve an IVP. From integrate, import, solve IVP, def ODE, x comma y, return y, solve IVP, ODE, let's do 0, 1, 1. All right, so that gives me a solution. I think that if I replace this here with SOL, also it's going to give me an error. We cannot serialize that particular variable. So we can only serialize with JSON, the most generic vanilla data structures, and nothing too much more complicated. Now there is something called OR.json, I don't know. And it is able to do a better job of serializing. And so this is the OR.json library. It's a little bit tricky to use with NumPy. It claims to serialize these things natively, but it turns out that we need to do a teeny tiny thing that I have to look up almost every time. And that is to use this option. All right, so it looks like we just import OR.json, we make some data, and then we ask it to serialize it. So let's have a look real quick at that. Let's take this dictionary and turn it into some data, into a variable. All right, so this is going to give me that error. Let's see what happens if I just do this out of the box. That still gives me an error because it says NumPy ND array is not serializable. And so to solve that, I have to go back to here, copy this option, and pass it. So we have to say option equals this, and dictionary key must be a string. So that is a new problem. So again, we're not going to be able to serialize everything, but let's make this a string. And lo and behold, it is able to serialize it. Now, it serialized it in a way that does have the data, but it's not actually that easy to reconstruct the solution object. So we can see here you get a variable that's got null, and then it's saving all these attributes on it. So it is saving all the data, but not in the same way. So we're not going to be able to access it with like sol.t or sol.y. So actually that's not so true. If we get E, we're going to get a dictionary that has all of these solution properties. So the dictionary does have T and Y, T events and things like that, but it's not exactly the same. But it still might be useful. And this is going to be JSON data, and so this will make it interoperable with any language that can read JSON if we can write this out to the hashcache library. So next time I think I'll work out a way to use something like this. Let's try one more, something that is not obvious to me should work, because this will be an atoms object. and in fact it does not work. So this is not a JSON serializable atoms type, but we could call the .toDict function that will make it work, where we have some representation of the atoms object. So we're obviously not going to be able to save everything using hashcache this way, but we can save a lot more things, and we can save them in a JSON format with pretty minimal effort at the end of the day. And then the only question is whether, like, how do we improve on the searching? Because so far I've only showed you linear brute force search, where you read every file, check what's in it. And what we'll look at next time is integrating this OR.json serialization into SQLite with JSON searches from SQLite as a potential tool for caching this work and making the data findable, interoperable, and reusable. Seems like a lot of work to get there. But nobody has done this work yet in a way that I use it on a regular basis. And even this project has been ongoing for many years, and we're still kind of getting to the end there. Okay, so let's let me make myself a note. We're going to integrate OR.json for serialization into hashcache with storage in SQLite and searching from JSON. All right, these little to-do items are actually really helpful. In Cymax, I can run nb agenda and see a list of all the to-do items that I have in here. And so we have these I can jump around and get to. So I have some ideas in molecular simulation. Once we work out a good hashcache solution, then I'm going to test it out using some molecular simulation ideas. I ordered this self-driving lab light demo, and so that's going to be another application where we communicate with a remote instrument and run it and do experiments. And temperature control lab is similar, a little digital instrument that I want to explore and try out. I haven't fixed this thing with named results yet, and this next time is what I wrote here. So I can do a lot of things with Cymax and Emacs that make it good for project management and doing experiments. All right, I'm going to stop there, and we'll pick up next time and look at using hashcache. We'll write some custom functions and give it a test run and see how it goes. All right, thanks for